Hi, my name is Chris, and I'm a postdoc and associate member of ML4Q. And you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computing cluster answer questions about their role in the cluster, their research, and the future of quantum. In today's episode, I'm talking to Christian Gogolin and Gian Anselmetti, who are in-house scientists at Covestro. We discuss solving chemistry problems on quantum computers, research in a company setting, and the PhD student-supervisor-relationship. It is my pleasure to welcome Christian Gogolin and Gian Anselmetti on the podcast. You two are in-house scientists at Covestro. Let's first get it out of the way. What does Covestro do?
Yeah, so Covestro is a worldwide operating chemicals company. It is not very well known in the general public because it's been going under that name only since 2015. It used to be part of Bayer and has actually, or predecessors of the company have actually invented two very broad and important classes of plastics that are used in high performance applications in a broad range of industries. We're producing raw materials for for polymer production. So this is materials that our customers use to make high performance plastics materials.
So how does Covestro have a quantum R&D department?
Yeah, so Covestro has a digital R&D department, which is a more broadly focused department consisting of a few dozen people worldwide who are supporting Covestro's R&D activities by a broad range of simulation techniques on classical high-performance computers, simulating the products our customers make from our materials, the production processes of these materials, recycling processes of these materials, and so on and so on. And supporting R&D in a broad range of development questions. And this is a multidisciplinary team with simulation experts, but also data scientists. And since 2019, also a small but growing quantum computing research team.
Cool. So how are you two connected to ML4Q?
Yeah, so there's been a connection, like a personal connection between myself and ML4Q before there was the, so to say, connection on the company cluster level. In fact, right before I started working for Covestro, I was a postdoc here at the University of Cologne in David Gross' group. And I've actually known David Gross since, pretty much, since before I started my PhD, so for a long time. And we had common research interests in the areas of quantum information theory and quantum computing. And when I then joined Covestro, it was obvious that we would need a university partner to be able to, for example, hire PhD students like Gian and give them the opportunity to get a PhD degree while working for us. And so we needed a university research partner. And so we started working with David Gross' group, and then ML4Q sort of came on top of that.
So Gian, David Gross is officially your supervisor at the university. So how does this work? Is it that you meet him regularly, or?
I mean, that was the original plan in the beginning, and then the pandemic happened, and sort of this connection is not as usual as it was before. But so it is the general idea that sort of I keep in touch and sort of update him on the progress I make, sort of academically writing papers, all this stuff. And this will probably become more and more closer now that I'm sort of inching towards the finish line and sort of getting towards writing the actual thesis. And but sort of my scientific contact is mostly with Christian.
Cool. So within Covestro, how much effort is there on chemistry simulations? Does the company have its own computer hardware, its own experts? Like how extensive is this?
Yeah, so the company as a whole is pretty much research focused. So out of the, I don't know, something like 16, 17,000 employees, we have over 1,000 full-time employees are in R&D of some sort. Of course, only a small part of this is like digital R&D. But the digital R&D department globally employs, I think, something of the order of 50 people, as I said, of like distributed over a wide range of different backgrounds and simulation technologies. And yes, we do actually run our own on-premise HPC cluster that is administrated by people from our team. So yeah, it's a quite serious effort.
And Christian, for this, you have to also manage this part, or was this something that you just did have access to, but you have the separate quantum part?
Yeah, so the resources, the HPC resources, they are managed by people from the digital R&D internally. And yeah, we have full access to that for our quantum computing research as well.
And what does the company expect in the end? I mean, of course, this is not it's a significant investment, I guess. Would the expectation be that the products will become cheaper or more ecological, or would the products become better, or both, or all of them?
Yeah, so ideally, of course, in the very far future, at some point, all of that. But so this is not a prestige project for Covestro, and I've sort of made sure that it doesn't end up being one, but a project where people actually expect to see results at some point. At the same time, there's a very good understanding of the timescales on which this technology will mature. And so at the moment, we are very much focused on what I believe will be one of the first commercially interesting applications of quantum computing, namely the simulation of matter on a quantum mechanical level of molecules and chemical reactions. And this is sort of at the very bottom of this, like, I would say, tower of or stack of simulation technologies that you can use to simulate all sorts of different chemically, or answer all sorts of chemically interesting questions. And so this bottom layer of this quantum chemicals compute stack is actually not so much relevant for our products, because they are the properties you're interested in, they are typically manifest themselves on like larger length scales. And so you would use more like semi-classical methods, MD, continuum fluid dynamics, you name it. But the production and also recycling techniques are for those sort of this quantum mechanical understanding on a molecular level is important. So this is where I would expect quantum computing to have the first impact.
And is another like commercial interest in this in the form of IP?
Yeah, I don't think I can go into too much detail here, but we'll probably come to this later. We are working with some external partners, among them a quantum computing startup QCware, for example, which of course, due to the nature of their business, has a strong interest in protecting IP, and also we as a company file IP in the area of quantum computing.
So so indeed, if you have these external partners, also Google, right?
Yes. So we also have a sort of big multi-year collaboration with the Google Quantum AI team. We're now, inching towards the publication of our first sort of big joint work. Unfortunately, it hasn't quite made it over the finish line yet. Otherwise, I would be able to tell you more about that.
If so, the podcast will take some time to come out. If not, we will add it to the show notes. If it has come out by then. So about these kind of collaborations, how easy is it to form mutually beneficial partnerships, especially once you have IP and so on? Is this like a big part of your of the management part of your job?
Yes, absolutely. So this was, I would say, during my first year at Covestro, this was pretty much my full-time job, was going around screening the startup landscape, talking to people, seeing sort of what expertise was available in which startup. Because why do you partner with people? Because you think you need expertise that you don't have in-house. And so we put a lot of effort in the very beginning, very sort of carefully selecting the partners we want to work on and also the projects we want to work on. Because, I mean, there are certainly players in that field with much deeper pockets than we have. And so you have to carefully pick your battles. And we sort of picked a few sort of key projects that we think will deliver sort of important key technology and try to concentrate on that, and in that way become a relevant player in the field.
Very nice. So a few general questions. First, Gian, maybe how different is it to do a PhD connected to industry from doing a normal university PhD? I guess you have enough of an understanding of what the normal PhD is like to maybe illustrate the differences.
Yeah, that's a good question. At least the perspective I can give is I chose the path I'm on because I also did my master's sort of in combination with, I did my master's in Copenhagen and I worked with Microsoft Quantum on sort of Mariana Zero modes, to give some context about that. And what I liked sort of about the work there was that everything you did you did in a way that somebody else could benefit from the work you did. And sort of you made something that other people could build upon. And at the university, I was sort of missing that feeling in a way, that sort of people were working towards a paper or the next thing, and everything was made in a way that it would reach this very line, but sort of not further than that. And maybe that's also, in a way, I liked engineering more than sort of research, but sort of building something that then goes into something else, and you can sort of slowly inch towards a bigger goal. Maybe that's from like a higher perspective. From day-to-day work, I don't think it's that different. I don't have an obligation to teach, which is nice. But I think besides that, the work is maybe a little bit more applied than, for example, what is happening in David Gross's group. But from a principal point, I think there's not.
I guess one other difference is the people that you meet, right? Like, I guess at university, you mainly meet professors, but you also at the company have a bunch of professional, I guess, programmers mostly that you interact with more, I guess. Then is that helpful, or?
It gives you perspective, especially working with external partners and sort of seeing how they structure their work, sort of what they emphasize and what they do, what they consider important and whatnot. And then you look at your stack and like what you sort of figured out and didn't, and it's nice. You sort of sit at a crossroads and can see into everyone's hands what they're trying to play, and then you can sort of make something up that you think is best from there. But I wouldn't say you don't meet a lot of professors. Sort of like the quantum computation sort of people have also considerably moved into these companies.
Yeah,
and I think they would have taken like professorships in like normal scenarios, but somehow now ended up taking bigger paychecks from companies. I think that's probably one of the main motivations to go there. And so it's still like a very
you still meet the academic
bubble in a way.
That makes sense. And Christian, how is it to be for you? You also have, like, I guess, a lot of perspective on this, how it is to be a scientist in a company versus a scientist at the university. What are the differences for you mostly?
Yeah, that's I could give a very long answer to this one. So, I mean, a few sort of things maybe that stand out. So one thing that I really like about this position is the easy access to people working in computational chemistry. So this is certainly something that, let's put it like this. It's like, had I like applied for an ESC starting grant, or I have actually applied for an Eminuta junior group fellowship before making the jump to industry, it would have been impossible to write a grant that is so much at the intersection of those two fields, and it would have been impossible to hire, say, someone with a postdoc experience in computational chemistry similar to the expertise that we have in-house in a sort of newly founded quantum computing research group. So it would have been very difficult in an academic setting, I think, to bridge the gap between these two fields. And it's absolutely crucial to do that if you want to make like meaningful contribution to the development of quantum computing, that there's expertise in the target domain and in quantum computing at the same time. Then, like, another thing I very much like about this position is that at the moment, quantum, maybe not so much anymore as it was like 3 years ago, but still to a large extent, quantum computing is a technology that is maturing and looking for an application. And so being on the application side of quantum computing, on the side of what will become the future users, actually is a relatively comfortable and powerful a position in which many people want to talk to you and share knowledge with you and get in touch with you. And that also makes this position very much interesting and appealing. And thirdly, like one thing I was very much sick about in academia was like spending incredible amount of time on writing grants with extremely low success rates. So I did spend, I don't know, something of the order of 50% of my time over the last 3 years as a postdoc writing grant proposals for grants with sub 1% success rates. And that is just so incredibly wasteful and depressing, I must really say, work that I couldn't really keep up with that anymore. And I mean, it's not that I do no longer need to apply for money if I want to spend money. That's certainly, I don't want to give this impression here. But the mechanisms by which it is distributed and the success rates are certainly much more reasonable in an industrial setting.
All right. Yeah, that makes sense. I think for me also, in my work as an experimentalist, I often think that, for example, in our lab, in most advanced experimental physics labs with a quantum computing focus, it would be good, for example, to have some professional programmers or even some professional people in the field of electronics. And to be fair, as a university, we don't have the money to, or the sort of positions to hire a permanent programmer nor a permanent electronics person easily. And I think that really, like, for example, I mean, FPGAs is a compute, like many quantum computers are in some level controlled by these feed programmable gate arrays. They're kind of difficult things, right, to work with, and you would need to hire professional people to handle this, and it's, at the university level, it's really difficult. So I completely agree that for these things, companies are much better thing. So let's talk a bit about your backgrounds. Maybe starting with Gian. You did your master's in experimental physics, working on the Majoranas, as you already said, in the lab of Charles Marcus. How different is it to change from experimental physics to theory now in the PhD?
Yeah, in one way, I think it's fairly similar. In other ways, it's very different. So, I mean, for everyone who has spent some time in front of a dilution fridge and sort of taking measurements on there, you set up a measurement, you let it go, maybe it takes an hour, maybe you do it overnight, and then you get some data back, you analyze it, and then you sort of start over again. And that's actually, that part is not so different from sort of running benchmarks on quantum algorithm, where you also have a black box, which is sort of your simulated quantum computer, where you put something on, maybe it takes a day, maybe it takes for longer calculations, depending on how much compute power you have, it takes longer. You get something back, you analyze it, and then you sort of start over again from there. So at least this process feels very similar to the way I was working before. The things I actually miss are days spent in the lab, sort of actually doing something with your hands and sort of going there early in the morning, sort of spending all day in the zone in a way, having some good tune, like running in the lab and doing your thing. And in the end, you made something that wasn't there before. And then when you measure that thing and it's nice, it's even better. But sort of just making something physical, that's a bit what I'm missing. Now you write a lot of code, and then it tickles a different part of my brain. And then some test passes which didn't work before, and okay, now I'm sort of a step closer to my goal, which is also nice, but sort of nothing being there at the end of 3 years, sort of in physical form, is a bit of a weird feeling. So what have I actually done?
Another question, like maybe correct me if I'm wrong. I always thought that theorists need to be more confident, because as an experimentalist, if things fail, to some extent, many experiments fail because the success rate is low to begin with to make make one of these devices successfully. So there's a large component of luck. Let's say you can make a device every 2 weeks or something, and your chance of making a successful one is 10%, then there's really a lot of scatter on how many weeks you will work on average to get a success. Well, here, what is stopping you is really your own intellect.
Yes. You sort of your own bottleneck, and that's also a feeling you really have to get used to, because it's very weird in the beginning. It's like, if I was smarter, this would be easier. But that's sort of not the frame of mind you should have. So
okay, you sort of agree with this, that the theory is like, because in the experimentally you have an excuse, like,
and you can sort of
grind, is not good enough. You
can grind on things as well.
Yeah.
I mean, if you have a 10% success rate with your devices, you can just spend some time on it, and at some point things will work, hopefully. If it's not, you're doing something wrong, and you can reconsider. So
where's your magical spark of intellect that makes you see the matrix something?
Exactly.
Yeah.
Sometimes it's when you go for a run. Sometimes it's somewhere else. So it's inspiration is a lot different working on these sets of problems.
So this PhD project is about simulating chemistry. So what drew you to the topic?
I always sort of was fascinated with quantum algorithms because we had courses in quantum information back when I was doing my master's, and building the foundational blocks was nice and interesting in itself, but sort of the computational science end of things, actually having something that is considered an algorithm that then knows something more than you didn't before, was interesting to me. And I also agreed, at least for me, it was clear that chemistry, if anything else, is sort of the first, at least commercial hurdle these things are going to take in a way. I mean, we can talk about what impact quantum computers will have sort of on like foundational physics, and where they definitely will have an application. But sort of the commercial side of things, chemistry probably is the first one. And just working on these things and learning more than you knew before, I think it's just like the basic premise of doing a PhD, sort of just having the time or the luxury of spending some time learning something you didn't know before in a very detailed manner. Was very attractive to me.
Christian, what to you, what made Gian stand out among candidates?
Yeah, so there was no shortage of candidates, of applicants for that first PhD position. I can say that. What made him stand out? Well, first of all, okay, I guess this probably sounds terrible, but for an experimentalist, he had a very sound and decent understanding of quantum computing theory and the kind of Nielsen-Schwang type quantum mechanics that you need in order to grasp the principles. He also had a very good background in programming, and a lot of the day-to-day work that we do is programming. And so that combination, like people that have those two things to offer are in very high demand at the moment, and they were already in pretty high demand 3 years ago. And the third thing is, I guess, this mindset that John's actually been talking about before, that he brought with him from experimental science, this like willingness to build something so that other people can build on it, right? Because the deal is of these PhD positions is sort of that you get all the infrastructure that the group has already built, plus access to the HPC and access to the computational chemistry experts from the company. And in return, so to say, you help grow this infrastructure, right? And so you need people that enjoy growing this infrastructure and don't just want to work on their like little puzzle piece.
And there is also sort of like being the first PhD student where there is no lab in a way. So where you build the lab, that's also always also very nice because you can set up things like the way you would like to have it, and you're sort of not stuck with what's already there.
In the case of you guys, that is setting up a code base, right? Like,
yes.
I guess, and this, like, let's say software development, it's really a very strange art, right? I have the feeling that, I mean, I also sometimes we have coding problems, coding projects where we set up something and this structure managed to last for years, and sometimes you have something the way you have to rewrite everything every few months. Like, how is there, like, how do you learn this? How do you teach this?
Oh yeah, that's a good question. How do I teach? Okay, how do I teach it? You can ask Gian how I teach it. But yeah, I agree. That's very much an art. I mean, it's I guess it's something that comes from, I don't know, it's difficult even to describe sort of how it feels when you do it. It's like some people, when they're faced with certain computational problems, given their background, they have this ability, and you can learn it by practice. You have this ability to sort of zoom out of the problem and sort of see the bigger and bigger picture. And I guess an important part of this is seeing or being able to foresee how problems can generalize or might generalize. Then you want to set up your code in a way that it will be able to handle these future generalizations. And yeah, I mean, I don't think there's like a silver bullet to solving this. I mean, one thing that is like sort of almost a silver bullet is test-driven development, because when you have a decent coverage of your code base with what is called unit tests, it's like automated tests that check certain features of your code base, whether they still work, then you will be much less afraid to make big breaking changes, because you know that the features that you care about are still there and still work. And so this gives you the sort of confidence and flexibility that you need to make those breaking changes. Because I think no software infrastructure can be sort of perfect from the start. I think, like, looking back, I think we made a great number of really good decisions. We had sort of lengthy discussions and fights over software architecture, and I think they were very worthwhile. And I think we can look back and say we made some good choices. No?
Yeah, but I think there's no end where you can talk about code. We've always.
How much time do you guys spend, like, at a whiteboard or like at the level of PowerPoint, drawing boxes and arrows and stuff like this? Or
it's more on like a screen shared basis. Okay. So like directly looking at code, discussing, okay, we could do this. I really don't like this part. What's going on here? And sort of showing and then talking about it, because, like, again, a pandemic was upon us. Yeah. And we spend most of our time sort of working at home, and it's like it's about to change now. But sort of at least more or less the entirety of my PhD, everyone who I collaborated with was like a moving picture in a frame over MS Teams, which I don't know, now feels very normal to me, which is also weird. And like now I've started to actually be able to see these people in person, like actually know, okay, who are you and what do you do?
So like, oh wow, you're that tall. I didn't expect
exactly.
that.
Maybe Gian, one last coding question. Do you think after 2 years, you are now at the level that you look at, like, let's say you have I don't know, like you have some algorithm in mind, some calculation that you want to do? Are you now better at breaking this thing up into individual methods and building blocks?
Definitely. I think this is maybe the most important thing that you can do in a way. And yes, definitely. What I still find challenging is sort of the collaboration part of this work, where sort of it's not only your own code and you sort of have to do something in an existing part of the code. Yes, where you sort of are stuck with choices already made, and so maybe they are not aligning with what you would have done in the first place. So you have to sort of understand the whole scheme to be able to integrate these things. I think this is sort of even the next step after.
I think this is personal pet theory of mine, but I think it's impossible to write intuitive code alone. Like, I think in order to make something intuitive, you need to speak to at least one other person and ask them, do you think this is intuitive? And then they will say, I understand that part, but this you should.
I would agree.
Yeah, I would agree. I mean, yeah, maybe you can get away with sort of that other person being some sort of separate part of your own mind, but I don't think this is optimal. And we do this. I mean, we do not very rigorously, but we do most of the time employ sort of principles of pair programming, and we certainly do code review. Like every merge request into the stack is reviewed, and then the reviewer will tell you if what you wrote doesn't make any sense to them, right?
Yeah. At this point, maybe we will shift to your background, Christian, but just a public service announcement, maybe. I think if you are a potential bachelor or master student and thinking about these things, or still in your physics education, and there is an elective programming course, take it. And also, if there's some possibility to learn about software development on a level like Git or really algorithms, also take those courses. They are the most marketable skills you can have as a working theorist, and they will always keep you employed.
Yeah, of course, it depends. I mean, if I may say one more sentence of this, like, of course, this depends highly on the quality of the course, how useful they actually are. But the second thing that you can do, irrespective of whether there are good courses available, is get involved with some sort of open source project. Try to make even some sort of minuscule contributions to that, just so that there's some code of yours in some sort of public Git repository of some creditable project, and you've gone through the experience of doing that once. That really helps a lot. And use the I think you said the privilege of being able to sort of decide how you want to spend your time during your studies, and if at all possible, start some sort of small open source project of yourself, right? Be it some sort of trivial app or I don't know, whatever. You will learn so much in the process.
Yeah, I agree. I think especially if you're most people who listen to this will be interested in quantum computing in some way anyway, and it's really you won't get anywhere within the field with not good skills in sort of programming. So Christian, let's get to your background quickly. You did your PhD with Jens Eisert in Berlin. How did your PhD experience prepare you to be a researcher in the field of quantum information?
Oh, good question. Well, so the group of Jens Eisert, when I was there, was much smaller and much more sort of in the ramp up and getting started phase than it is now. And I think I was very lucky in the sense that I sort of caught Jens in sort of the optimal phase of his career. It was like at the time when he really still had time to spend hours with a newly starting PhD student in front of the blackboard, and I was enjoying that quite a lot. And so then sort of I was very lucky also in the sense that as I grew more proficient, the group became more and more globally visible, and so we had very good visitors. And so then through a scholarship I was able to travel a lot. So I was in this very fortunate situation that I could get a sort of very, I would say, complete quantum information theory education while being there, and could very sort of freely follow my own research interests, which at the time were always at this interface between quantum information theory and quantum computing on the one hand, and quantum many-body physics and thermodynamics, statistical mechanics on the other hand. And that was a great setup for me. I mean, back then I was working much more mathematically and much more theoretically than I'm working now. So I didn't do much programming during my PhD, to be honest. So that's something I've been doing like before actually starting my PhD. I've been programming a lot. Like my bachelor's is in classical computational physics, and I've been programming, I don't know, since the age of 8 or 10 or something like this.
So just about this thermodynamics, in a way, as we built bigger quantum computers, like the original small quantum systems and many experiments were sort of away from the thermodynamic limit. But as we make more quantum computers, we push more into this thermodynamic system, and we have to worry more and more about thermodynamics. Should we, can we think of things like error correction and so on as a cooling process to sort of preserve a system in a, like to sort of prevent a system from becoming chaotic?
Yeah, so I guess these kind of discussions, they can become sort of philosophical very quickly. I mean, as a sort of mental picture, I think this works very well. Then if you dig deeper, I think there's a bit of a mismatch of terminologies because, I mean, a quantum computer or anything that you may want to call a quantum computer is certainly a system that is not anywhere near thermal equilibrium. So it doesn't have something like a well-defined temperature. I mean, obviously the physical material out of which it is made has a temperature, but not the sort of logical components that you use to actually carry out the computation. And so I would be very careful taking that analogy too far, but it is certainly a useful analogy.
Okay, yeah, that makes sense. When I was writing my own PhD thesis, I was reading a bit into the history of the field, and I came on the work of Landauer, who was like writing about quantum computing in the 90s, and he was actually kind of quantum pessimist. And for example, he quoted quantum many-body localization as like an obstacle to, like he was saying, this will never work. There will be some sort of chaos and many-body localization, and quantum computers are bound to fail. I think by now we think this is not the case, but there is on the level of many-body physics, there's also some work to maybe be done to understand this, right?
Yeah, there certainly has been some sort of cross-fertilization between this, and I was working at this interface, but obviously I was one of many people working at this interface. So there's been a lot of cross-fertilization between these two fields. That's for sure.
And then you went to ICFO. Let's just maybe go over this quickly. How does the visit to ICFO is the Photonics Institute in Barcelona? You worked with Asin and Levenstein there. How did this shift your perspective? And like, is this like something which influenced you a lot?
Yeah, so I guess in a sense it was topic-wise, I think it was pretty much a continuation of what I was doing before. My motivation to go and work with specifically those two people at this institute was because, again, like the ASEAN group was more from the information theory side, and the Levenstein group was more from the many-body quantum optics side of things. And so I wanted to stay at this interface. Then at the same time, I must say that while I was there, it was really while I was there that that quantum computing proper started to become more interesting for me, because I'm with Landauer here that I was also for a very long time a quantum computing pessimist, and I thought that this was very interesting and academically to think about quantum information processing, but I never thought that I would sort of live to see this being realized. And then while I was there, IBM put their first machines on the cloud and so on. And I got to know Peter Wittek, who was sort of very well connected in the Canadian quantum computing landscape then already at this time. And so I sort of could see this coming, that this was becoming a real thing, and it was starting to become... It was starting to look like it could become an actual technology. And at that point, it started to become interesting for me, beyond sort of my pure academic interest in information processing. So
you're also connected to Xanadu quantum computing, right? Which is what's the official company?
Yeah, so I think the official name is Xanadu Quantum Computing Inc. It's a Toronto-based quantum computing startup that is working both on quantum computing software and their sort of flagship packages, the Penny Lane library, which is a library for variational quantum algorithms, quantum machine learning, and automatic differentiation of quantum circuits. And they are, the second thing they're doing is they're working on photonic quantum hardware. And so I was I was working for them part-time on top of my postdoc work for some time, and I helped to develop this version 0.1 of Penny Lane before it came out. And so I have no formal affiliation anymore with them. But of course, I know people there, and we are sort of power users of dependency and software stack. And we are still in contact regularly, obviously.
Cool. So in a sense, really, this postdoc was the time where you sort of shifted more into this application mindset of quantum computing. And basically, now you're running a quantum computing department in a company, which is as applied as it gets.
Yes, yeah. I guess you can, in the broader sense of the term, you can think of us as a sort of quantum computing startup inside of a big company, right? I mean,
Yeah. So I had you guys fill in some separate sheets with questions ahead of time, and maybe we can go over some of them. So they are a little bit, they are mean questions about the PhD student-supervisor relationship. But I mean, let's start on a lighthearted note. I asked, you are more annoyed by people claiming that a quantum computer A solves chemistry and B solves problems by just trying out all possible answers. You both really came down on B. I guess this is something. Yeah,
it's a bit of a trope. I mean, like by now you heard it so many times, and if you know it's wrong, it's just it's like judging any, like, I don't know, publication and sort of in the public realm about these things, and it sort of happens in at least in the first couple of lines, and you know if it's actually worth reading or not, and you can so please, everyone, don't. It's not true. Please don't use it. Thanks.
I mean, solving chemistry is also
but it's sort of.
It's more true, maybe.
I mean, they can behind like solves chemistry. They can hide a lot of things. I mean, what's actually solving chemistry? It's not like state of. It's misleading in a way, but it's not maybe flat out wrong than the other option is.
In terms of the supervisor-supervisee relationship, we have Christian as a supervisor is A, too close, and B, too distant about micromanaging, sort of. And it's really interesting because Gian said too distant and Christian said too close. So there's there you guys sort of disagree.
Yeah, so my theory is that I'm aware that I tend to micromanage, and I'm working on doing this less. And Gian is a very independent person, so I'm using him a lot to practice. So that makes sense.
That does make a lot of sense. I mean, you both think that you as a supervisor are too detail oriented, but I think that's normal. I mean, okay, that I think I would say more. I mean, once you start writing the paper, everybody's probably too detail oriented.
I liked it. I mean, I wouldn't have it any other. It's very important to be
detail oriented.
Yes. Yeah, I've heard this actually as a sort of criticism from some people that what you're doing there, you're worrying too much about the details. And if I look at sort of how other quantum computing labs are run at big companies, many of them are certainly much less detail-oriented than we are, but this also means that when you hear them talk about quantum computing, there's lots of misleading or wrong statements being made by those people. So, yeah.
I also asked some mean questions about the PhD student work. I mean, it's not so long ago for me either, so I can do. I asked Gian, should A, work harder on his code, or B, spend more time reading the literature? And I mean, Gian crossed both, but you crossed the literature, and we have to say, in your field, the literature is brutal.
Yeah, the literature is absolutely brutal. Like, it's developing so fast, it's almost impossible to keep track. Why did I cross this? Because now that he's sort of approaching the end of his PhD and he's done a lot of sort of hard work coding things up, I think it's a good moment to before you sort of reorientate yourself to look around a bit. So I would encourage him to spend a bit more time reading papers.
Yeah. You also, I also had as Gian as a PhD student should A, listen more to advice from his supervisor, or B, work more on his own ideas, and you both click B, so you are now at the stage where you're becoming more of an independent researcher. How does it feel?
I mean, it's nice in a way, but it's also frightening because there comes certain expectations from others and from yourself. It's like, okay, now I should be able to spread your wings and do your own thing, and eventually it will probably get to that. But it's a I don't know. It's a weird feeling to sort of consider yourself being finished with a PhD at some point in the near future.
I also put some questions about coding behavior, and you both agree that Gian writes the more performant code and Christian writes the more understandable code. Do you think that understandable and performant code are mutually exclusive?
Yes.
To some degree, yes. I mean, I guess if you want to write really performant code, you write Fortran. That's certainly not very understandable. But I mean, to a large extent, I think this has been alleviated by sort of nice multiprocessing and just-in-time compilation and GPU libraries and so on. And Python is a very sort of nice language in the sense that it's very easy to write understandable code. But I'm almost, I would say, obsessed with writing understandable code, and I'm extremely nitpicky about variable naming and so on. But I also regularly see people sort of shooting themselves in their own foot and like wasting a week or two just because they named a variable so that the variable name does not actually reflect what the variable contains. And then like when they go back and a few months later want to modify their code, they think the variable contains what the name says. And then, everything goes off the rails. So that's why I'm so nitpicky about it.
I also kind of agree. Do you think that it's more important to write documentation lines in the code or to pick smart variable names and function names?
Definitely the latter. Yeah. So we write doc strings, but we try to keep them pretty minimal, and like nobody should be afraid of like 20, 30 character variable names as long as they're descriptive. The good thing about it, code changes, right? We've discussed this before, and usually documentation does not change. Like people forget to change the documentation when the behavior changes, but it's very much more difficult to make it's more difficult to oversee having to change a variable name when you change the functionality than it is to remember to change the doc string when you've changed the functionality.
Yeah.
But I mean, by now, both of us, you've been there for a while, but we're both very opinionated about code structure, and it's not aligning every time. And sort of Python is in a way a very wacky language. If you can break everything, if you care about, so it leaves a lot of room of what you can do. And then most of the discussions we have is sort of, should we use this feature which sort of saves us maybe some code duplication, but has trade-offs in other ways of readability and so on and so on. It's nice to sort of migrate from, I think, the discussions we had when I started to sort of very sometimes esoteric questions about how to structure a part of the code and sort of what's the best tool to actually get what you need. And it's nice.
Okay, maybe I'll skip some of the chemistry questions because we get to them quickly soon. But maybe just one thing, I let you also write down the year where you think the first commercially viable quantum computer will be available. And Gian wrote 2030 and Christian wrote 2035. So the more experienced person pushing it out a bit further. But I think actually you're not, you're just 5 years apart. That, it would have been also possible to pick 2050 or 60.
Yeah, I guess it depends a lot on what your definition of commercially viable is, right? If it's just like you can sell the thing, or is it like, can you sell it for more than it costs to make the thing? Or is it like, is it solving important enough problems that sort of justify all the development effort until that point, right? And I guess I took it a bit as like, when I think there's a good chance that it will be sort of foreseeable that quantum computers will be able to solve problems that are sufficiently important that the development effort of the past decades was actually justified.
Because indeed, some companies already sell quantum computers. And okay, there's probably no company that is even close to break even in selling quantum computers. But okay, but let's now get a little bit, we have to try to explain it, like to try to give a big picture view of quantum chemistry. So to what level can we say chemistry is just applied quantum mechanics? Would you guys agree with this, or?
I would disagree. I think I would have agreed before I started the PhD. Now I very much disagree. There's things where you need a chemist, period. Where even, we spend a lot of time in this area, but I think we're physicists, and then nothing can change that by now. And you can understand the algorithms, how to get one thing, and you can understand the other algorithm that does another thing, and you can get every step how you get to where you're going. But then you need a chemist intuition at a lot of points where we're just looking at things. Okay, you have to make a decision now on what to do, and we can't do it. It's like choosing orbitals, and there's a lot of like black magic going around, and you have to sort of
let's maybe preface exactly.
Be in that environment, and that I think you will need that even in the future.
So let's maybe preface things. Like, I guess it's unfair to say that you would solve chemistry, because in some way the complexity of the possible compounds in chemistry that you can make, even just of carbon, hydrogen, and whatever, like simple organic chemistry is insane. And there's no computer that could even just search for all the possible compounds, right? So you do need to have some practical guide. You have to know where you're looking. It's not,
Yeah, you absolutely have to know where you're looking. Then sort of having more reliable, more advanced simulation techniques that give results that you can trust also in sort of more unusual cases certainly helps a lot. And I guess my hope is that it will allow chemists to leverage the sort of more obscure properties of certain elements and certain compounds that are presently sort of not really even known or used, because there's no methods to understand what they would do in the given scenario. The chemical space is certainly far too huge for there to ever be a sort of, I just solve chemistry, I dump all my results in this database, and then from that point on, chemistry is just sort of a search on this database. This is never going to happen. And this is, I guess, interesting, because this really means that sort of ab initio computational chemistry simulation, so simulation from first principles, will probably forever remain an indispensable tool in this area of research.
Yeah. So let's maybe state the problem for the listeners. So the structure of the problem is that we have some nuclei and we have electrons. Is that the right way to start?
Yeah, that's the question sort of on what. So I was talking before about this sort of stack or hierarchy of different simulation techniques that simulate chemistry on different length scales, because chemistry can mean many different things. It can, for example, mean understanding, extreme example is maybe understanding the mechanical properties of a foam from its chemical composition and the process conditions under which it was made. And that is ultimately a completely classical problem. And it's extremely difficult to make this connection. And if your definition is that this is part of solving chemistry, then you have to sort of take all of these higher level methods into account. But what we are focusing mostly on, particularly in this area of quantum computing for chemistry, is this part of chemistry where the quantum mechanics of the electrons, mostly of the molecules participating in certain chemical reactions, has a more sort of immediate effect on quantities that you care about as a chemist. And yes, there the name of the game is essentially what you just explained. So you have molecules that are made up of these positively charged nuclei surrounded by electrons. And this is a priori, or at the beginning, this is like a terrible problem, because you have the coordinates of the nuclei in principle are quantum coordinates. The coordinates of the electrons are quantum coordinates. All of those fly around in three-dimensional space. It's a continuum problem. You cannot even, it's not even a discrete problem that a computer can solve. So that's sort of where you start from. And then you sort of go down this ladder of like making more and more and more and more approximations until you have something that you can put on the computer and ultimately solve.
How many electrons can we do on a classical computer right now?
Yeah, that's sort of not a super well-defined question, because the problem, or the question is always sort of with what level of accuracy. Yeah, okay. So the further you sort of descend down this ladder that I just described, the more approximations you're willing to make, the larger systems you can treat. And so what you will typically end up doing is a sort of you use your chemical intuition to understand in which parts of your system which effects actually matter, and then you will try to describe sort of as much of your problem with these cruder, more or less precise approximations that are faster and less resource intense, and try to use the most precise and most resource intense methods only for those parts of the problem that actually need this precision.
Just as a stupid experimentalist question, for all of these approximations, is it easy to bound the errors, or
no?
To know basically, no. to basically know I've made this approximation, that means I'm still at least 1% good near the right answer? Or?
No. And mostly you don't even know, like you usually don't even have a guarantee that, for example, the energy you're getting out after this approximation is certainly above the true energy or something like this. Like usually you don't even have those kind of guarantees.
So it's tough. It's a tough problem. Huh?
It's a tough problem, yeah. And then on top of that, you're often not interested in, say, the energy per se, but typically you're interested in something like an energy difference, right? So the energy difference between what we call the reactants, so the starting sort of molecules of your chemical reaction, and the energy of what we call the transition state, which is sort of the highest, energetically highest state you must pass through to sort of reach your products. That is a large part of what determines the rate at which this chemical reaction can happen, or the temperature you need to get it going. And so you're interested in this difference of these energies. And these differences of these energies, they are typically absolutely tiny compared to the absolute values of these energies. So you're trying to estimate, tiny differences between gigantic energies.
Just bad limit to be in computationally.
Yeah.
So, but I mean, people have done, like, let's say computational chemistry is a very mature field, because I mean, I've heard this number quoted that 20% of the world's supercomputing time is spent on, like, order of 20% is spent on chemistry problems. So it must be like, it's something that, of course, is really relevant. How much, like, let's say, so we will talk about the quantum computer part next, but still just as a stop, how much is the classical computing part in chemistry a moving target? Like we say the quantum computer will become have a quantum advantage, but the classical computers not only improve, but also the algorithms improve.
Yeah, so this is very much a moving target, I would say. I have the feeling that over the last few years, progress in classical hardware was quite a bit faster than progress in classical computational software. In particular, there's several cases where it's sort of in principle known that one could write an implementation for certain widely used methods that would be much faster than the implementations that are currently in practice actually being used. And that's true to some extent both for the state of the art in industrial R&D, but to some extent it's also still true even for the state of the art in academic R&D on that topic. So yeah, this is very much a moving target, and I'm looking forward to seeing sort of what the next few years will have in the cards about this.
Just a very quick question: is there mathematical proof that sort of solving a lot of the currently relevant problems is impossible on classical computers, or do we just have a hunch that we don't find a good heuristic?
Yeah, that's a good question. So there's very different answers that you can give. So there's like a computer science answer that you can give, which, for example, there are like hard complexity theoretic results about certain chemistry problems that relate, for example, to this gigantic chemical space that you mentioned before. Or there's also complexity theoretic results about finding exact exchange functionals in DFT, for example, that sort of in a way prove that these algorithms are classically hard in some sense. But those results are often sort of not very applicable. They're often sort of worst case complexity results, and they're often sort of not directly applicable to the actual problems at hand. And I mean, I guess there's still a lack of imagination here. There could still be some sort of silver bullet approximation that somehow magically makes all actually practically relevant chemistry classically easy. But I don't really expect this to happen. I mean, very smart people have been working on computational chemistry now for a few decades, and while there's still progress, I mean, it's not that like a new sort of breakthrough method appears every year. I mean, the reality is that a lot of chemistry is still done with DFT and is still done with DFT functionals that have been around for a few decades, and people are using them because nobody was able to come up with something that works better. So yes, and these methods certainly still do have shortcomings and known shortcomings in some cases.
So okay, in comes the quantum computer, and on the quantum computer we have, is it fair to say, like two main algorithmic paths towards quantum chemistry? Or like two main algorithms. There's the quantum phase estimation algorithm and there's the variational quantum eigensolver. Is that?
Let's say we have two that we can discuss today.
Yeah, okay, I guess there's more. Yes.
Yes. And I mean, I guess the one where we spend most of our time is the variational quantum eigensolver one, which started off as a bit of a crook to make use of current devices. Because like quantum phase estimation sort of ends up with having longer circuits.
Meaning basically when the first, like, let's say when people started writing papers on this 10 years ago, they couldn't do quantum phase estimation because it's too complicated.
Exactly, because you're limited by your coherence time, so you just cannot implement the circuit as long as it's needed. And you still can't, in a way, it's still not quite there. And then people figured out, okay, I don't have to actually implement time evolution, or like, I don't have to do this on my machine. I can sort of trade this in for shots and sort of just measure in different bases and then do this often enough and then reconstruct visual Hamiltonian from these shots and get a result as well. And then I'm sort of free of I have much shorter circuits I can actually do on machines.
But you need a classical computer to do another part.
And I think this is sort of the main takeaway that VQE has provided the field in a way, that no quantum computer will exist in a vacuum and do its own thing. It will always be a part of a bigger thing, working in tandem with, say, a CPU and probably a GPU and maybe a TPU. So it's just one more processor where you can offload calculations that are faster on this architecture than it is on the other ones.
Maybe if I describe it just briefly, so you make a guess about what you think, like let's say the ground state of your system is like, and your quantum computer calculates for your guess what the energy is.
Yes. So the guess, in a way, is as with always in physics, people like Ansatz says, and that's also what you use in here. You either use the operations your quantum computation platform provides you and just tile them out and hope they make a nice guess when you parameterize it, or you look for sort of nicer way of spending your wheels or like your knobs you can turn to increase or make your wave function guess better. And then you start off maybe in a random point or not, and then you can sort of ask your quantum computer, okay, what is the energy of this configuration I just set up at these specific parameters? And then your quantum computer happily tells you with some precision. And then the classical computer is using some sort of optimization algorithm, which then has, similar to like the machine learning part of things, tries to figure out, okay, I'm on a optimization landscape, where is my next step? I should go from here to lower my energy. And then you sort of move step by step to hopefully the lowest energy of this landscape, sort of guided by your variational principle that you cannot go below if you make things right. And then hopefully end up in the lowest possible state of this configuration, which hopefully is close enough to your ground state that you can make use of it.
I think maybe I'm remembering this wrong, but there was early paper, like this was one of the first things that people could do once they had 2-qubit quantum computers, right? But it's fair to say that some of the initial papers cheated a little, right? Or maybe cheating is the wrong way, but they sort of already knew what the solution was, so they could make the algorithm simpler, right?
Yes, I mean, this is always, there's a lot of sort of classical pre-processing that you have to do or can do to make the quantum computer as easy as possible. And the reality is that, yes, I mean, you would always want to solve as much of the problem as you possibly can classically before you then solve the hardest remaining part on the quantum machine. That certainly is a sort of fair way of looking at it. But then, you have to be a bit careful about sort of how you interpret the results, because if you are making sort of simplifications along that way which are sort of chemically not reasonable, like choosing a very small basis set, for example, to describe your system, or sort of using in very extreme ways certain symmetries of your system that you would never have in like a real problem, then the resource estimates that you get out of this, they can become sort of unreasonable. But in principle, this is fair game, I would say.
Okay. So your work in the last years has been partially to study this algorithm with like some examples and to figure out, you have been working on what's on the Ansatzes and also on just trying to understand how well it actually performs in some example settings.
Yeah, so a lot of, I mean, these variational algorithms, they are heuristic algorithms in the sense that you can't essentially prove anything about them. You don't have any performance guarantees. And so to answer this question that we're all interested in, namely, will quantum computers without error correction be able to solve problems that are, say, commercially relevant? What you have to do is you have to try out how well do these heuristics work in practice. And that is not so easy because simulating these devices is very costly classically. So simulating the quantum computer that solves the problem you care about is much harder than just solving the problem you care about. So there's this big gap between the problems that where you can still simulate how the quantum computer would solve it, and the problems that you cannot solve anymore by any means. And you want to extrapolate beyond this point of where your classical computer cannot solve the problem anymore at all. So you at least want to have some data points, sort of say, in between, right? So you really have to push your classical compute power to get some sort of reasonable idea of like how the performance of these methods will continue.
What's the factor that we need to extrapolate here? Like how many, like factor of 100 in qubits or?
Yeah, I guess now it's more like a factor of 10 or something in qubits. Wow. But I mean, the problem is the classical compute scales exponentially. So if you're asking about, say, Hilbert space dimension, then this is like many orders of magnitude. But yeah, I mean, you can do a sort of reasonable classical simulations for, I don't know, some 20, in some cases maybe 30 qubits. And problems, like exact solutions, are no longer available classically in many cases beyond like already for something like 50, 60, 70, 100 qubits for sure. So in chemistry, you're not actually that far away. Like if you handed me like a quantum computer with, say, 100 but perfectly working qubits and also very fast, perfectly working qubits, one could already like do stuff with that, which would be very difficult to repeat classically.
Yeah, so Gian, one of the questions, you guys have done both, right? You simulate a simulator, well, you simulate a quantum computer, and you also use some computing time on some quantum computers. How does this differ, and what is like? Is it important to do both? What do you do more? How is this?
I think we're at a point in time. I mean, like simulating a perfect quantum computer is hard enough. I mean, especially if you push it to like higher qubit counts. I mean, it's the main thing, the main reason why you build these things. But simulating a one with errors is even harder than having a perfect one, which sounds counterintuitive, but sort of have to simulate all these processes that lead to the error in the first place. And then you have to sort of consider the error models you actually put into the simulator. And it's a lot of work sort of to simulate an error-prone quantum computer on classical hardware. And now the devices that people can build are at a point of like size where it's actually worthwhile trying to run like smaller versions of your algorithms on chip with some error mitigation to see how they all the theory you've built up so far in sort of a vacuum now performs on chip, and if the method that simulate-wise worked nice actually leads to better error mitigation or not. So like a lot of things are like open questions until you put it on chip and see what it does.
Have you tried the difference between coding up your problem in a stupid way on the quantum computer prototype and coding it up in a smart way? Or
In the end, that's what you end up doing. Yeah. Yes.
So and how important is the smart sort of the compiling of the quantum program?
It's very. It takes longer than you think. There's a lot of minor details that you don't think about in the first place, and you inch towards a better solution, one error source at a time.
So you would say that working practically with quantum computer prototypes really also is an important thing to learn about them. It's
probably the main use of the NIST devices, if you ask me.
I don't know, we're getting close to the end, but I do want to ask, like, maybe because you guys are in a company with many of the real people who have been working on chemistry problems for a long time, I guess. Are they impressed by you guys, or are they sometimes amused? Like, what is the relationship between the hardcore computational chemists and the quantum computing department?
Very good question. What's your perception, John?
I think it's gotten more serious, at least over the time I've been there. I mean, like, for me, it's still we solve problems that we can just solve in, like, I don't know, on a laptop in a couple of seconds. But I don't know. I think we're being taken serious. That's maybe the one takeaway I have.
Yeah, I would second this. I would say they are seriously curious. This is something that I think the whole field of computational chemistry, and that includes the applied people who are working in companies, they are sensing that there's this new technology which has the potential of, like, turning the field upside down, essentially, making things possible that look completely ridiculous today. And they're very curious to learn what the capabilities are, and we are very curious to tell them sort of what the capabilities are and hear how useful they think they may be, because it's very easy to get carried away. Like, you think I have this machine that can solve this and this problem, this gotta be useful. And then you talk to someone who's, like, actually doing computational chemistry and say, like, wow, that's actually not the bottleneck here. Right. So this conversation is very important, and I'm very happy that we have curious people on the other side.
I think it's fair to say that you actually do find probably the better computational chemists in industry than in academia, right? I don't know how much this is true, but I mean, it's technically, if you're really, really good at this, it's actually very valuable, like, in terms of money, right? Like, to some extent, some computational chemistry has a very high.
Yeah, so the first part of the question I cannot answer because I've hardly ever worked with computational chemists in academia, unfortunately. Yeah. The second question, I would say yes. But surprisingly, I think the realization how valuable computational chemistry can be in an industry R&D context is still relatively young. Like, given that DFT was invented, like, in the 70s, it's still sometimes surprising me somehow how not so widespread this.
Yeah, okay, and it's true. I should not forget to mention there's also probably more chemists who just work in the lab and try things out, and they also find ingenious solutions. So I think it's also that's maybe also an important aspect, that of course the quantum computer might push the field a bit, but to what extent we should expect that we find solutions that people haven't stumbled upon already is also an interesting question.
Yeah, and I'm not so worried, because already with the tools that the computational chemists have available today, they are able to make very meaningful contributions to the development of chemistry. So this is something that is already working very well. And so giving those people much better tools will certainly make them much more productive. I'm not worried about that part.
Okay, cool. Then, okay, I think we have talked a lot now. Thank you guys a lot for your time. And it was a pleasure to find out more about research in industry. And, really, thanks a lot.
Thanks for having us.
Of course, yeah. Thanks very much.